Hello everyone. Today we will be discussing about recursive languages, church thesis and P and NP type of problems. So the topics which we will be covering in these slides include recursive and recursively enumerable languages, Chomsky hierarchy, church thesis, P and NP type of problem. We have discussed in these slides of Turing machine that there are three possible outcomes: halt and accept the input, halt and reject the input, and never halt, that is loop forever. A language is recursive if there exists a Turing machine that accepts every string W and rejects every string that is not in the language. That is, machine M halts in final state if W is accepted by the language, and machine M halts in non-final state if W is not accepted by the language. That means we have only two states. One is accept state and another is reject state. Next we come to recursively enumerable languages. A language is recursively enumerable if there exists a Turing machine that accepts every language and does not accept string that are not in the language, but it may cause Turing machine to go into a infinite loop. So machine halts in final state if W is accepted by L, and machine halts in non-final states or loops forever if W does not belong to L. Such languages are also called Turing acceptable and Turing recognizable languages. The recursive enumerable language is called Turing recognizable, whereas recursive is called Turing acceptable. What is the difference between recognizing and deciding? Turing recognizable is that it will enter accept state, or it will enter reject state, or it will never terminate. And Turing decidable is one in which machine will enter either a accept state or it will enter a reject state. So this is how we represent them. Every recursive language is a subset of recursively enumerable language, which is further a subset of non-recursive language. One of the most important topics of theory of computations, which actually concludes this entire course, Chomsky hierarchy, defines the language in terms of types: type 0, type 1, type 2 and type 3. Type 3 is finite state. The language which is acceptable is regular, and the automata which is drawn corresponding to type 3 is finite automata. Next we came over to context free. The grammar is context free, the language is context free, and the automata which is accepted is push down automata. Then we come to type 1. In type 1, grammar is context sensitive and the automata is linear bound machine. And in type 0, we have grammar which is general rewrite. We have unrestricted language, and the automata which accepts is Turing machine. Please remember that every language of type 3 is also of type 2, 1 and 0. That means 3 is subset of 2, 1 and 0. Likewise, 2 is a subset of 1 and 0, and 1 is a subset of 0. We represent it diagrammatically. Type 0 represents recursive enumerable. Type 1 represents context sensitive. Type 2 represents context free, and type 3 represents regular language. Now we come to Church-Turing Thesis. It asserts that if some calculation is effectively carried out by any algorithm, then there exists a Turing machine which will compute that calculations. So the basic crux of this is that any mechanical computation can be performed by a Turing machine. There is a TM n corresponding to every computable problem. Set of languages that can be decided by a Turing machine is identical to set of languages that can be decided by any mechanical computing machine. If there is no TM that decides the problem P, then there is no algorithm that solves the problems P. So in the crux, we can say that for every computational problem, there exists a Turing machine. Hence, we say that all of these statements are implied by Church-Turing thesis. Before discussing P and NP type of problems, let's discuss how the execution time of an algorithm is computed in computer science. Computer science is largely concerned with a single question: how long does it take to execute a given algorithm? But scientists do not answer in minutes or milliseconds. They give it relative to number of elements the algorithm has to manipulate. Algorithm's execution time is thus directly proportional to number of elements it's handling. Many common algorithms have execution time proportional to n square or n times the logarithm of n, etc. Come to P and NP type of problems. First, we will discuss what are P type of problems. P is set of problems that are solvable in polynomial time by a deterministic Turing machine. If algorithm run in linear time, that is order of n. Say for example, we have linear search or quadratic time, order of n square in insertion sort, or cubic time, order of n cube in a 3x3 matrix multiplication. Then we say that algorithms run in polynomial time, and The problem is solved in a class P. What are NP type of problems? NP means non-polynomial. NP is a class of computation problems for which solutions can be computed by non-deterministic Turing machine in polynomial time. Or equivalently, those problems for which solutions can be checked in polynomial time by a deterministic Turing machine. Thus, we can say that it is not necessarily a polynomial time way to find a solution, but once you have a solution, it only takes polynomial time to verify that it is correct. Please remember, one of the important properties of NP type of problems is that they can be solved in exponential time. There are two types of NP problems. One is NP hard, another is NP complete. NP hard problems are the problems which are hard to solve, and even if someone gives an answer, it is very hard to verify they are correct. Best example for NP hard problem is move in a chess game. We cannot verify that whether the move which was taken is the correct move or not. If a problem is NP hard, this means one can reduce any problem in NP to that problem. Please remember, this indicates that if we can solve any NP hard problem in polynomial time, we always compare it with the other problem and we say that since X problem can be solved, Y problem can also be solved easily. If we could solve a NP hard problem in polynomial time, this would prove P is equal to NP. All NP complete problems are NP hard, but all NP hard problems are not NP complete. Now we will discuss NP complete problems. NP complete are the problems that are tough to solve but easy to verify if a solution is correct. Say for example, the Sudoku. Vast majority of NP problems whose solutions seem to require exponential time are called NP complete, meaning that a polynomial time solution as one can be adopted to solve all the other problems. A very good example of NP complete problem is a traveling salesman problem. Given n cities and distance between them, can you find a route that hits all of them but in the shorter time? A diagrammatic representation of NP. P is a subset of NP. A problem is NP complete if it is both NP hard and NP.